introduce Manuela Zoccali, because in addition to being an outstanding scientist, she is also one of my real best friends. Actually, we know ourselves since many, many years, since when we were, let me say, extremely young. So let me give you some information about the academic achievements of Manuela. Manuela got the degree in astronomy in 1995 at the University of Padua, with the supervision of Professor Piotto, with the thesis concerning the stellar population in a galactic globular cluster. After, in 2000, she got the PhD in astronomy in the same university with the same supervisor, defining a series of observational constraints for studying the evolutionary and dynamical properties of Loma Star. After that, she spent a 3-year PhD fellowship at the European Southern Observatory in Garching, and then a 1-year fellowship, the so-called Princeton Pontificia Università Cattolica Prize Fellowship, in between the University of Princeton and the PUC in Santiago. In 2004, she became staff member at the University at the PUC in Santiago, and since then she has always worked inside this university, and since 2017, she is full professor in this university. She is also deputy director of the Millennium Institute of Astrophysics. Concerning the scientific interest of Manuela, she is one of the more expert researcher in the field of resolved stellar population, but in particular, more specifically, she is one of the most worldwide recognized expert in the study of one of the most intriguing, let me say also mysterious component of the Milky Way, that is the bulge. And in fact, today, Manuela is going to talk about the stellar population of the galactic bulge. So please, Manuela.
Many thanks, Santino. Really nice introduction. Yes, as Santino said, in fact, I'm going to talk about the galactic bulge. I put inner Milky Way instead of bulge in the title because I like to start my talks with the definition. In this talk, I will use the word bulge to indicate, in fact, just a region of space confined in more or less 2 kiloparsecs. Depending on the study, one might extend it to 3 or to 1, but it's basically the central region of the Milky Way. There is a difference. I want to specify that just because, as we will see, there are many components in there. So when I say the word bulge, I don't mean to differentiate it from the bar or anything like that. I'm just specifying a region of space with whatever is inside, except the region around the black hole. That's why I have a red cross in the middle. I will not dive into the nuclear star cluster and into the black hole science. So let's start with some motivation why I am personally interested in the galactic bulge. The reason is that the bulge is massive and the bulge is old. These two characteristics mean that this is the first important component that formed in our galaxy. Because the halo, for instance, is also very old, but it makes up more or less 1% of the mass of our galaxy. So even if we understand completely how the halo formed, we still have in place only 1% of the galaxy. We are far away from having the whole galaxy. Instead, the bulge is more massive and is also old, so it is really one of the first things that formed. What do we know at the moment about the formation of the bulge? I downloaded this infography from 20-year-old ESA press release from the Space Telescope. And here in this press release, there are cartoons of 3 possible scenarios of bulge formation. The first one, it's a rapid collapse that used to be called monolithic. It's now, I would say that it's now completely abandoned. And these 2 scenarios, environmental effect and internal evolution, have been really like the two main alternative scenario of formation almost until today. The first one is an ex situ scenario in which the bulge formed much like a small elliptical galaxy by merging of extragalactic fragments. And the last one is a formation in situ in which the bulge, usually not very round, maybe more like bars, formed from material from the disk in a scenario driven by dynamical instability that was understood to be relatively slow. That's why often it was referred as secular evolution. Right now, as I said, the first one is, I would say, obsolete, but we are converging in kind of an intermediate scenario in which, for sure, we know that we have a bar. So our galaxy resembles perhaps more like the last one at the bottom right. However, we know that the formation is definitely not slow. And there is something, we think, that is reminiscent of this merging of clumps, because we need to reconcile what we see in our galaxy and in nearby galaxy with what we see in massive star-forming galaxies at sea at high redshift. In particular, there is this study by Forster-Schreiber about a large sample of galaxies at Z2, that means about 10 giga-years ago. Those are future spiral galaxies that are forming a lot of stars right now. And these maps are in H alpha, where H alpha is tracing the actual star formation. These galaxies have dense clumps of very high star formation across their disk. And many of them, like this one, for instance, already have a bulge in place. What this is telling us is that galaxies like our own form stars in dense clumps in the disk that eventually coalesce in the central region. So it is a little bit like this, except that these dense clumps are in the disk. More or less like that, I anticipate that is what we think is happening, but of course we miss a lot of detail, not so small, in this scenario. In order to justify my personal interest in the bulge, I said that the bulge is massive and the bulge is old. I would like to expand a little bit on these two statements to convince you that they are true. The first one is that the bulge is massive. I report here several recent determination of the mass of the bulge. Our own with Elena Valenti, 2 × 10⁻⁻⁻, solar masses, and other ones, 1.5, 2.4, 1.8. I think we all agree. If there are differences smaller than a factor of 2, I think in astronomy they are completely negligible. But in fact, we agree pretty much, because the reason for these differences is more the definition of where are the limits of the bulge, because of course the bulge is not an isolated component. So some of us take all the stars within 2 kiloparsecs, some other of this study define a bar with 3 axis length. And so when the definition changes, of course, the final result changes. I want to draw your attention to the fact that this order of magnitude is about 1/3, even more, according to some author, of the mass of the disk, which is most of the mass of our galaxy. So we are talking about really a major component of our galaxy. Regardless of the fact that you can measure the mass of the bulge with several different methods, including most of them are dynamical methods, I want to stress the fact that our own method is something unprecedented. I don't want to argument if it's better or worse of the other, but for sure, it's something that we can do now for the first time and only for our galaxy, which is a completely empirical determination of the stellar mass of our bulge just by counting stars in this region that has been mapped from the VVV survey. Because we can count stars really one by one, of course, we also have an estimation of the completeness. So we are aware that we can miss some part, but we can estimate how many we miss, pretty reliable. Then we can also construct the density profile and the mass profile. So we can estimate the mass inside the region that we want. And this is extremely powerful. And of course, it is possible only in our own bulge. It has been possible for us, and it's possible for you as well if you want to play with counting stars in your favorite region. There is a public stellar catalog with PSF photometry in J and KS, near infrared bands, with also completeness and with reddening, all of the whole bulge region mapped by VVV. It has been published and made available through ISO archive by Francisco Surot, Elena Valenti, myself, and Santi was also involved in this work. So I think this catalog is really very, very powerful, and it's good that you know that it exists. The second thing that I said is that the bulge is old, and let's expand on this. In fact, the bulge is mainly old, we think. The issue of the age of the bulge, or more likely the age distribution of the bulge, is still a debated issue. And the reason why it is debated is that it is really complicated to constrain the age distribution. This is because what you're seeing here is an example of one of the best color magnitude diagrams that we have for the bulge. It has been obtained with the Space Telescope. You see here the main sequence, the turn-off corresponding to the old population, about 10 giga-years ago, and the red giant branch. This specific color magnitude diagram has been decontaminated by the disk stars that are in the foreground. Of course, when we look at the bulge, we have the disk in front. If we want to study a poor bulge population, we have to remove the disk. And how the best way we have to remove the disk is with a kinematical decontamination based on proper motions. This diagram here that we are looking at has been decontaminated already. But as you can see, there are stars in this region that could be either a non-perfect decontamination from the foreground or intermediate age and perhaps young stars that have a turn-off brighter than this one. And so the community is divided between some people, including myself, I am co-I of all these works, that think that the bulge is mainly old and this stuff here belongs to the disk, or they are blue stragglers of the bulge. And these people here that think that those are intermediate age stars. Of course, we both have arguments to claim what we claim, and it's really hard to, or it has been proved hard to reconcile these two positions. I want to emphasize that the kinematical decontamination of the bulge from the disk is not easy at all, because the proper motion distribution of bulge stars, here depicted in red, and the proper motion distribution of disk stars, here depicted in blue, largely overlap. So you cannot make a cut that leaves only bulge stars in one side and only disk in the other side. It is impossible. And this is due, the spread of those two distributions is not due to the errors that could eventually be reduced with a longer baseline. This spread is really the intrinsic velocity dispersion of the two components. And so it will be hard to solve this controversy with this method. Really, there is an intrinsic problem in the analysis of a pure bulge population. So one of the main work that produce some tension concerning the age of the bulge is the work, the many works actually by Bensby and collaborators, in which they obtained high-resolution spectra of dwarf stars very close to the turn-off in the moment in which they were microlensed. So they were greatly amplified, their light was greatly amplified, and therefore they could obtain a really high-resolution spectra. From the high-resolution spectrum, they would derive the log G, the gravity, and the temperature, and then they would put it in an HR diagram with an isochron and derive age, which was possible because those dwarfs are very close to the turn-off. As a result, they obtained this age metallicity distribution, in which we could look at this plot by drawing a line here, more or less, and conclude that the metal-poor stars are mostly old, more or less older than 10 gigayear. Instead, the metal-rich stars here above have a broader age distribution, and there is a non-negligible fraction of them that are younger than 6 gigayear or 7 including, and a few of them are even 2 or 1 gigayear old. Really, we do not see so many intermediate and young stars in the turn-off. Even if we consider that all the stars above the turn-off could be young stars, they would not be such a large fraction. And so there is tension between these two results. We still do not have an argument to believe that this could be wrong, but it is impossible to reconcile this result with the study of the CMD. Another approach that might shed light is this one by Hasselquist et al. 2 years ago, using data from APOGEE. What they did is to analyze about 6,000 RGB stars, because they are target of APOGEE, that is an instrument on a small telescope. They need to be bright RGB stars. So they are all located in the upper RGB. They derive, again, effective temperature and log G from the spectra, and age from the isochron. Actually, they, of course, because there are 6,000 stars, they do not analyze them one by one, but they use the canon, a data-driven code, based on a training set. And the training set, the age of the stars in the training set is constrained with this method by deriving ages with isochrons. What they found is that in this plot, that is a bit complicated, but I'll try to make it simple, you have metallicity in the x-axis and the fraction of stars younger than 5 gigayears on the y-axis. So their conclusion is that, and the lines of different colors correspond to different height from the plane. So the blue curve represents stars closer to the plane, within 0.25 kiloparsec. Those blue line shows that at supersolar metallicity, you have more than 50% of the stars younger than 5 gigayears. But for more metal-poor stars, you have most of the stars old. When you get farther away from the plane, so you go to the cyan or green or red curve, the fraction of super metal-rich stars younger than 5 gigayears decreases. I think that this method is, or a method similar to this, is promising because it doesn't require to solve the problem of the decontamination at the turn-off that I explained, that is very hard to solve. However, I would like to know the opinion of Santi, that is here, about the determination of the age in the upper RGB for stars of supersolar metallicity. First, because the stars in the upper RGB, we know that are not very sensitive to age. The isochrons are not, so if the models are not sensitive to that to begin with, I think it's difficult to derive ages for the stars. But also I'm worried about the fact that isochrons are calibrated on data, and there are not so many stars with metallicity plus 0.3, with which people could calibrate isochrones very well. So I think it's really the way to go, to try and derive ages for individual stars in the bulge, but this is really difficult, and I'm not sure that this specifically is, that we are there yet. I mean, that we can obtain reliable ages yet. Santino, let us talk about this later. So to make, I will make through this talk what I like to call a running summary. So to fix the idea that, that I mentioned, if we construct a metallicity distribution of the bulge, and we think that we have one side that is the metal poor one and another side that is the metal rich one. This is an adaptation from a metallicity distribution from Álvaro Rojas Arriagada here in the audience. We demonstrated that the metal poor side is only old. We all agree on that. While the metal rich side has an important old component, but we don't agree whether there is also some fraction of young stars or not. To progress, this image is this image here above is an artistic image of our galaxy taken from a recent review from Shen and collaborators. Of course, it is an artistic picture, but it is based on the latest, our current understanding of the 3D structure of our galaxy. And what we see is that in the region that we are analyzing here, the bulge, or the inner region, there is a prominent bar. The fact that in our galaxy there is a prominent bar was already known since the Vauboulaire in the 60s, and it was already clear with the Kobe-Dirbe maps of our galaxy, like this one at the bottom of the figure, because it was asymmetric, as you can see. The left side was more bright than the right side, and this was correctly interpreted as due to the fact that the left side is closer, while the right side is farther away because of the presence of a bar. This has been studied and measured many, many times since the 60s, and our current understanding of it can be resumed by this picture. This picture is taken from Weg and Gerhardt, 2013, who analyzed red clump stars in VVV data. There are several newer measurements based on updated version of the catalogs that found very similar things. It's just that I like this picture more because I think it's clearer. According to latest measurements, the axis ratio of the bar is this one. Here we have the semi-major axis of a bit less than 1 kiloparsec. And the angle of inclination between the major axis of the bar and the direction between the center of the galaxy and the sun, this phi, we think it's more or less within 20 and 30 degrees. Many of the measurements converge on some 27, in fact. The whole bar as a pattern speed velocity means that it rotates. It has a bulk rotation with a velocity of about 30-40 kilometers per second. Me and Elena Valenti in 2016 wrote a review about the 3D structure of the bulge, in case you're interested. The way these maps and these measurements are derived in these works in particular is using red clump stars in the bulge, stars in this region, burning helium in the center, as distance indicators. The reason why red clump stars are often used as distance indicators is because we know that they have very little dependence on age, at least for ages older than 1 gigayear, which we all agree that is the age of the bulge. So let us keep in mind this. Most of the reconstruction of the 3D structure of the bulge is based on red clump stars. Further, in addition to the bar, in the outer region, we know that there is a boxy peanut shape, sometimes called the next shape, as Andy McWilliam and myself called it in 2010 when we discovered it. The presence of this boxy peanut structure is revealed by a double red clamp in some specific line of sight. For instance, from the sun, if we look at this line of sight, we cross two overdensities of stars, one here and another one farther there. That's why we have two red clamps. Many people have studied the same thing, we all agree, except that it has been proposed by a group of Koreans that this double red clamp could be due instead to a stellar population effect. I don't want to diverge too much in giving argument against that. I just want to mention very briefly that the killing argument for that scenario is that not only the two stars in the two clamps have a different spatial distribution, but they also have different kinematics. This is a clamp, and this is another clamp, a red clamp, color-coded according to proper motion. They have different proper motion, which agrees with the fact that along the arms of the X shape, you have streaming motion in different directions. And also, if you build a map of proper motion, in particular the correlation between the proper motion in longitude and in latitude, it's a complicated formula. For me, it is complicated, but dynamists understand it very well. If you make the map, you see a quadrupole, really consistent with a dynamical segregation of these two populations and not separation that could be due to different helium abundance or something like this related to stellar population. So I think it's really a strong argument against that possible scenario. We also know that in addition to the bar, the main bar, and the boxy peanut, our galaxy has a thin, long bar like this. Very thin and very long, extending up to about 5 kiloparsec in each side. This has been found by Wegg and collaborator in 2015, again with VVV data, and also verified by other people later. So the fact that this is the structure of our galaxy is not surprising at all, because already in 2002 and in 2005, Patsis and Lea Tanasula had published what was the natural evolution of bars in galaxies, and they found that it happens very often that the central part of a bar undergoes dynamical instability that induces an oscillations of the orbits. So the orbits that are the orbits of the star that are elongated along the bar start to bend down and up, something like this. This is a figure taken from Patsis. And so they generate the boxy peanuts. So the long bar and the central bar and the boxy peanuts are all part of one structure that naturally takes this papillon shape because of pure dynamical processes. And also we see this structure in many external galaxies. So it is not strange, it is not unexpected, and it's nothing especially weird that is present in our galaxy. It is something that we understand very well. But of course, we don't understand very well everything. Things are a bit more complicated. In fact, if we draw the metallicity distribution in different directions, as we did, for instance, in 2017, we see that it is bimodal, at least bimodal. So there are two components that when we move, each of these panels correspond to a different direction, a different latitude in our galaxy. If we move in latitude, the two components stay there, but the relative ratio of stars in each of the two varies. This has been verified by many people, in particular Álvaro Rojas Arriagada and myself and collaborators in 2020, argued that if you increase the statistic, increase the number of stars, here we had 13,000 stars instead of 5,000, formally you need 3 Gaussians to fit the metallicity distribution. As I said, I'm a co-author of that work. I am fully convinced that formally, if you want to reproduce this distribution with Gaussians, you need 3. However, for reasons that will appear clear in the rest of my talk, I tend to believe that perhaps each component is not a Gaussian, because there are several other arguments in favor of only bimodal distribution, at least in this region, and not of the presence of a third component, especially because the 2 components have different properties, but the hypothetical third is just intermediate between the 2. It is not distinct in any other dimension. So let's progress for the moment with the idea that we have 2 components that could be separated with some overlap in metallicity. If we analyze the spatial distribution of these 2 components, we see that the metal-rich side is very boxy, while the metal-poor side is more spheroidal. And the mass ratio of these 2 components is about 50-50. So this is really intriguing. We should find a way to reconcile this with all the study of red clump stars that I mentioned before. Because we know if we use red clump stars to reconstruct the 3D structure, we think that our galaxy is boxy, actually boxy peanut, as a bar, that seen at John is a boxy, as a thin long bar, etc. But we know that there is also a spheroid there that makes up about half of the mass. So perhaps those studies should be updated, or I don't know, made more sophisticated to include the presence of the spheroidal component. And I want to expand a bit on this with this view graph. I have to apologize for this view graph. Normally, I like to keep my view graph as simple as possible. And this is very dense. I don't like it, but but I couldn't avoid it, I think. So I'll try to draw you to this best as I can. Johnson et al. And Lim et al. Used data from a Blanco Deccan bulge survey that was in the Sloan filter, covering a pretty large bulge region. They demonstrated that for red clump stars, there is a correlation pretty tight between the U-I color, the reddening, and metallicity. They demonstrated the existence of this correlation because they had high-resolution spectra for several red clump stars, which are here marked in color. So these plots just demonstrated that U-I depends strongly on metallicity, is a tracer of metallicity. Assuming this, let us go and see the distribution of red clump stars in U-I in the y-axis, in the x-axis here, versus k, in different directions. Here there are 9 panels corresponding to 9 different regions in the bulge. What we see with contours is that the U-I, the red clump is always bimodal in U-I. See, there is a red blob and a blue blob in all of them. So there are 2 blobs. It's not a continuum. It's bimodal in color. It's a bimodal in a color that depends on metallicity. So it's bimodal in metallicity. But what they find that was not found before so clearly is that the red side, so the metal-rich side, traces a bar with a boxy peanut, because on this side, which is this side, the red clump is brighter than the metal-poor side. That's because this side is the nearby side On this other side, the red clump, metal-rich red clump is fainter. And in the middle, you have two of them, because you have the boxy peanut. Now I draw some lines. In the red side, you see the red clump is bright on this side, faint on the other side, and in the middle, you have both. Because in the middle, you cross the two arms of the X shape or boxy peanut. Instead, the blue side, the metal poor side, has a red clump always in the same position. You see, it doesn't move. So not only the metal poor stars do not trace a boxy peanut, they also do not trace the bar. So the picture that we were seeing, reconstructed mostly by Weg and Gerhard, that we have a bar with a thin long bar and with a boxy peanut, is telling only half of the story. There is another half, that is the metal poor half, that is axisymmetric. Why they didn't find it? Why, when they analyzed the red clump, did not find another component? Because they were using near-infrared color. And it is only in this specific color that you get a bimodality in color, because you managed to split the two metallicities. They had no metallicity indicator, and so they would sum in this clump to this other one. And that's why I think they couldn't separate it. Let us summarize then. We have that the metal poor side is only old, while the metal rich side is old and maybe with some young component instead, or maybe not. We also have that the metal poor side is spheroidal and the metal rich side has a bar and a boxy peanut. We also know that these two sides have different kinematics. The metal poor side rotates slower. It rotates. It has some rotation, but it is slower than the rotation of the metal rich side. And also the sigma is different. The velocity distribution is different because the metal poor side has high and constant velocity distribution. Instead, the metal rich side has a gradient, a marked gradient with latitude in the velocity dispersion. This has been found by several people. This is just an example by Rojas and Regada, using radial velocities in spectroscopic surveys. But it has also been confirmed by Clarkson et al. Using proper motions. Clarkson et al. With space telescope data could use a combination of filters that separates the stars in metallicity. And by using proper motions with space telescope, they could trace the velocity, the rotation velocity of the metal poor stars that is flatter than the rotation curve of the metal rich side that is more steep. So summarizing again, the metal poor side rotates slower, while the metal rich side rotates faster. And this side is a constant sigma, while this other side is a gradient in sigma. I should speed up. So there is a last thing that is different among these two components, and it is the ratio of the alpha element over iron. Again, Alvaro demonstrates that the distribution of magnesium over iron versus iron, it was bimodal, had two blobs. He had, I don't remember, a few thousand stars in this plot, but Queiroz et al. More recently analyzed of the order of 20,000 stars from APOGEE and with distances from Gaia DR2, and they found that really several alpha elements combined versus iron is bimodal everywhere. And again, the ratio of the two components changes with position in our galaxy. At the high latitude, the metal poor side, high alpha, dominate. And when we get closer to the plane, the metal rich side, low alpha, dominates. The same is visible with more statistic, of course, on a larger region. So putting this in our summary, The metal poor side has also high alpha over iron, while the metal rich side has low alpha over iron. And again, let me go back. This is the strongest argument, in my view, in favor of the fact that we have only 2 components and not 3. Because really this thing is, I think, clearly bimodal. But perhaps each of these is not really Gaussian. They don't have to be, there is no strong reason to believe that their shape should be Gaussian. So we have this situation on the side of the data. How can we interpret that? Perhaps we have 2 bulges with 2 very different origins. It would seem not, because the theoreticians, in particular Victor De Battista and collaborators and Francesca Fraguti and collaborators, demonstrate that you can get something like this with a metal-rich component resembling the bar with the thin bar and the boxy pin, and a metal poor component more spheroidal, with a completely in situ scenario in which this component comes from the part of the disk that has the smallest velocity dispersion. We can think about it as the thin disk if we want, while this other side comes from the part of the disk that has a higher velocity dispersion, and so it ends up on a more pressure-supported structure. This is what Victor thinks, and something similar is what Francesca Fraguti thinks. I mean, not thinks, demonstrates with their simulation, that you can get something like the bar more elongated and more boxy from the thin disk, and something more spheroidal from the thick disk. So we do not require that the spheroid comes from external merging. It can form in situ. How much time do I have? Nothing, I think. Right, Santino? So I had some open issues for the future, but I think we can leave it for question and discussion, and I could perhaps just put my summary. Give me a second. Here. My summary, I want to keep the summary simple. So is that the bulge contains at least 2 components, but both of them seem to have formed in situ, although through different star formation histories and different dynamical process. This is something that probably I will tell you in a different talk. That is the fact that we still know very little about the nuclear bulge, this region here, that is different from the rest of the bulge, not only because it is much more dense, but also because it has a central molecular zone. It has a large fraction of the dense molecular gas of our galaxy. And so the story there is different. There is a current active star formation, and the story of this part of our galaxy is to be studied separately from the rest of the bulge. It is especially interesting because an environment so dense in gas and so dense in stars, it is from several reasons similar to the environment in star-forming high-redshift galaxies. So we could understand a lot of external galaxy by studying this region, and we can study it with details only in our own galaxies. This is what we are trying to do at the moment, but